No rotational variability in C 2014 UN 271. Bernardinelli-Bernstein at 23.8 AU and 21.1 AU as seen by TESS. Abstract. The recent discovery of a 100-kilometer scale comet C 2014 UN 271 Bernardinelli-Bernstein has provoked interest in the activity displayed by such a large body inbound from the Oort cloud. We examine the serendipitous observations of UN 271 in long cadence imaging by the TESS satellite in 2018 and 2020, while Bernardinelli-Bernstein was at 23.8 and 21.3 AU for any notable periodicity, where an AU is the average distance from the Earth to the Sun. Bernardinelli-Bernstein does not display detectable rotational variability above the noise level in these data. Introduction. The inbound Oort cloud comet C 2014 UN 271 Bernardinelli-Bernstein was recently discovered at 29.3 AU in an archival search of dark energy survey imaging acquired between 2014 and 2018. The estimated absolute magnitude at discovery was HV equal to 7.8 mag, which implies a diameter between 130 and 260 kilometers for geometric albedos between 2% and 8%. While Bernardinelli-Bernstein's orbit is typical of its dynamical population, it is the largest Oort cloud comet yet discovered in the era of telescopic observations. Its size is more typical of the well-characterized trans-Neptunian and larger Centaur populations. Characterizing its physical properties will thus provide insight into the activation of a remarkable incoming comet. Bernardinelli-Bernstein was recovered in archival imaging from CFHT, Pan-STARRS 1, SkyMapper, and confirmed to display cometary activity at its current distance of 20.18 AU following rapid follow-up observations by the Alceo GT Look Key project and SkyGEMS Namibia. However, these data do not quantify the comet's rotation rate. Section 2. Potential rotational variability. Since Bernardinelli-Bernstein is of trans-Neptunian object TNO size scale, but within the dynamical population of comets, it may have physical properties across a wider range than just those seen in comets. TNOs of comparable size typically display rotational periods of 4 to 14 hours with up to half a magnitude amplitude of variability. It is worth noting that continuous photometric observations of centaurs with K2 have shown a population of very slow rotators with periods longer than 20 hours, and even up to 56 hours. Unlike TNOs and inactive centaurs, the rotational periods of long-period comets are difficult to quantify because the nuclei are obstructed by the surrounding coma. Alternatively, methods typically analyzing recurring features in the coma have revealed that long-period comets can have rotation rates spanning from 6 to almost 60 hours. The rotational light curves of Jupiter family comets are well measured and cover the rotational period range of 5 to over 40 hours with a typical observed amplitude of 0.5 mag. Section 3. TESS observations of C 2014 UN 271. Bernardinelli-Bernstein has been within the field of view of the Transiting Exoplanet Survey Satellite, or TESS, from 2018 September 21st to October 18th at 23.8 AU, and again from 2020 August 26th to 2020 October 21st at a distance of 21.3 and 21.1 AU. Thus, high cadence 30-minute exposure full-frame imaging exists for TESS sectors 3, 29, and 30. Note that the TESS observing cadence generates a 2-day gap between sectors 29 and 30. A deep stack of the earliest imaging, TESS Sector 3, showed Bernardinelli-Bernstein already exhibited cometary activity at 23.8 AU. While the activity may obscure nucleus-derived variability, we examine the TESS photometry for any rotational variation. Despite the high cadence, since Bernardinelli-Bernstein has relatively low signal-to-noise In individual TESS frames, these observations are insensitive to short-period rotational variation. However, TESS data well characterizes long-period rotators, for instance in the main belt asteroid and Jupiter Trojan populations. Section 4. Light curve analysis. For all three TESS sectors containing Bernardinelli-Bernstein, we create 250 by 250 pixel cutouts of the full-frame images centered on the midpoint of the path of Bernardinelli-Bernstein across the sector. We initially reduce each sector using the TESS reduce pipeline, which subtracts a variable TESS background, aligns images, and subtracts a reference image. We augment the standard TESS reduce source mask, which is generated using the Gaia source catalog, with a 9 by 9 pixel mask centered on the position of Bernardinelli-Bernstein in each TESS frame. The light curve for Bernardinelli-Bernstein was then extracted with a moving 3 by 3 pixel aperture. We then conduct a secondary background subtraction by interpolating over and subtracting the center of an annulus with an inner and outer radii of 5 and 9 pixels respectively. Finally, to remove any residual systematics that arise from poor subtractions, we use the previous process to calculate light curves leading and trailing Bernardinelli-Bernstein by 16 hours. We shift these light curves so that they spatially align with the light curve of Bernardinelli-Bernstein and subtract the mean of the two light curves. To reduce noise, we average the light curve by using a 2-hour median stack of frames centered on Bernardinelli-Bernstein, taking the error to be the standard deviation of the averaged frames. Figure 1 shows the sector track, resulting subtractions, and Gatsby-Lomskagel periodogram of the light curves for sectors 3 and 29 plus 30, searching for periods from 5.5 to 60 hours. No clear peak is detectable, implying that Bernardinelli-Bernstein does not have sufficiently substantial rotational variability to be visible above its activity at these heliocentric distances. Example light curves in Figure 1 correspond to a 2 times the best period to check for the double-peaked light curve typical of an elongated comet nucleus. Brackets 13.8 hours and 11.5 hours in sectors 3 and 29 plus 30 respectively, close bracket. As Bernardinelli-Bernstein continues inward towards its 2031 perihelion at 10.98 U, it will occasionally come once again within the field of view of TESS, helping to monitor its activity in detail.